Hey everyone, welcome back to The Explainer. If you're a focused learner totally ready to break free from the sluggish limits of high-level programming, making that jump from a standard basic user to an absolute master of the 6510 processor, well, you are in the exact right place. Today, we're literally unlocking the secrets of direct hardware control. It's going to be awesome.
Okay, here's a really quick look at our agenda for today. We'll start with basic versus assembly, then move right into logic operations. After that, we'll hit bit shifting and the carry flag, take a look at the bit instruction, and finally, wrap up with how to write clean assembly code.
Let's just dive right into Section 1, Basic versus Assembly, the ultimate architecture clash.
So the sheer contrast in processing speed here is, well, it's pretty staggering. I mean, if you've ever tried to write a fast action game in BASIC, you already know the frustration, right? BASIC is kind of like that sluggish snail. It wastes literally hundreds of clock cycles just mediating and translating your commands. But assembly is the rocket ship. It executes operations in just 2 or 3 processor ticks. Why? Because you are directly commanding the hardware, no middleman.
And look, it isn't just about raw speed. It's really about absolute memory efficiency. When you start manipulating bits directly, a single byte isn't just some number between 0 and 255 anymore. It actually transforms into 8 independent, highly efficient hardware switches. Think about that. You can turn 8 entirely different game features on or off using just one single byte of memory. That saves a massive amount of space.
All right, moving right along to Section 2, logic operations. Think of these as your filters and switches. Now think of the AND operation just like a series circuit in electronics. Both switch 1 and switch 2 absolutely must be closed for the light to turn on, right? If either one is off, you get a 0. In programming, this makes AND the perfect tool for what we call masking. We basically use it to multiply unwanted bits by 0, which effectively erases them, while keeping the bits we actually want perfectly intact. It's super handy.
Or, on the flip side, acts way more like a parallel circuit. If either switch is on, boom, the light shines. This lets us safely activate specific bits without breaking the surrounding configurations. And then we have EOR, exclusive OR. Imagine a super strict security door that only grants access if 2 incoming values are completely different. If they match, the door stays firmly shut. This makes EOR an absolutely incredible tool for instantly inverting bits.
The actual proof of all this is right here in the truth table. This shows you exactly how these logical filters instantaneously manipulate binary inputs right within the hardware registers. In BASIC, you'd have to write out some clunky command like print A and B, but in assembly, these logical gates process the bits directly inside the processor itself. You're definitely going to want to take a mental snapshot of this table because it is your ultimate map to binary logic.
Okay, Section 3, bit shifting and the infamous carry flag. Let's get into it. So before we can actually put bits into motion, we really need to understand the carry flag. When you slide 8 bits to the left or to the right, that bit on the very edge has to go somewhere, right? It can't just vanish into thin air. So it falls right into the carry flag. Think of it as a temporary holding drawer or like a spillover bin. This flag is our absolute crucial safety net for doing precision arithmetic.
You can really see the practical difference when we actually start shifting these bits around. With ASL, that's arithmetic shift left, pushing everything to the left gives us instant multiplication by 2, just like that. And with LSR, or logical shift right, pushing everything to the right gives us rapid integer division by 2. It is incredibly fast math, and the best part is you're not relying on any complex, super slow division algorithms.
Let's just trace the journey of a bit for a second and watch really closely for overflow here. During an ASL, everything shifts left. If a 1 happens to be sitting in that final slot, bit 7, and it drops into the carry bin, well, your result just exceeded a single byte. It is now larger than 255. Anticipating this exact overflow, that is exactly what separates the beginners from true hardware masters.
But hey, what if you don't actually want to multiply or divide? What if you just want to smoothly animate a character sprite moving across the screen? Well, for that, we use rotations, specifically ROL and ROR. Notice how it forms a closed loop. The bit that fell into the carry drawer loops right back around into the empty space on the exact opposite side. It's this continuous, recycled flow of data that is absolutely perfect for scrolling graphics.
Moving on to Section 4, the BIT instruction. We like to call this one the detective.
So normally, if you want to check a value in memory, you have to load it into your main workspace, the accumulator. But doing that completely overwrites whatever you are currently working on, which is super annoying. The elegant bit instruction completely bypasses this. It acts just like a magnifying glass, sneaking a little peek at bit 6 and bit 7 of a memory location, and it instantly sets the overflow and negative flags without dirtying your accumulator at all. I mean, it is just pure efficiency.
All right, let's actually test your understanding of the status register with a really quick scenario. If the comparison result of that bit instruction is exactly 0, what value does the processor give the Z or 0 flag? Just think about that for a second.
Okay, the huge aha moment for beginners is right here. It is reverse logic. A Z flag of 1 actually means the 0 state is true. Makes sense? If the result is not 0, the processor sets Z to 0, which means false. Wrapping your head around this reverse logic is, well, it's an absolute necessity if you want to create branches and loops in your code.
Finally, Section 5, Writing Clean Assembly Code and Formatting Rules.
Look, to make your raw silicon instructions actually readable to human eyes, you have to format your code carefully. The golden rules are actually pretty simple. First, format your code with strictly right-aligned comments so they don't clutter up the actual instructions. Next, maintain visual vertical alignments for your binary data so you can quite literally see the bits shifting. And finally, always prepare your carry bit.
Let's actually look a bit closer at that last rule. Think of this as your processor's dashboard. Before you write the code to shift bits, say to move that sprite we talked about earlier, you absolutely must use CLC to clear the carry flag, or SEC to set it. If you forget to manually flip these switches, your rotation is going to pull in leftover garbage data from some previous operation, and your graphics are going to glitch out big time.
I really love this quote. Understanding binary logic isn't just memorizing new syntax, it is an entirely new way of thinking. That pretty much perfectly sums up our whole journey today. By mastering these direct manipulations, the logic filters, the flags, the bits themselves, you aren't just a user constrained by high-level languages anymore. You are a full-blown architect, directly commanding the machine's nervous system.
So I'll just leave you with this final thought. Now that you actually command the absolute speed and logic of the 6510 processor, what impossible hardware effects are you going to build first? Seriously, take these binary concepts, apply them to your own retro programming projects, and push the machine to its absolute limits. Keep experimenting, and we'll catch you on the next explainer.